Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my honor today to present the host, Andrei Kolobov. This is actually a job interview talk. This is coming a little bit off cycle for the our typical hiring season pattern. We thought we'd take a first crack at Andrei before he opens himself up to other organizations. And Andrei was a star intern on our team 2 summers ago, and we've known him for years through our association with the University of Washington. He's been doing some really great state-of-the-art work in decision-making under uncertainty in situations where we think about sequences of actions and some notion of optimizing a long-term goal. Typically, this is in intractable spaces we'll hear about, and lots of good work has been going on to make these problems more tractable. Andrei did his undergraduate degrees in math and computer science at Berkeley, came to Microsoft to do a 2-year stint as a program manager, I guess.
As a developer.
Oh yeah, sure, sorry about that. As a developer in our desktop search team, and then went off to University of Washington to do his doctoral work. He'll be finishing up probably, I'm guessing right now, as one of his committee people, early winter. So this is we're getting an early look. Thanks, Andrei.
Thank you for the introduction, Eric. As Eric said, I'm a 5th year, at the end of my 5th year in the Ph.D. program at the Computer and Science Department of the University of Washington. And my talk today is going to be about my main research topic, planning under uncertainty, about the kinds of real problems that we can solve with models of planning under uncertainty, with the challenges in this field, and about the work I've done to address these challenges. Okay, so first of all, what is planning under uncertainty? Right, planning under uncertainty generally involves an agent, say a robot, that's acting in the environment. And what happens here is this agent gets some sensing about the environment, some percepts about the environment. And based on these percepts, it's trying to select a sequence of actions. So every time it gets the percepts, it's asking itself, what's the next thing I should do? Chooses some action, executes this action, the environment changes, and essentially the process repeats. Okay? Now, planning under uncertainty, we allow the environment to be dynamic. Okay? We allow things that essentially are outside of the control of the agent to happen, and we allow the agent to reason about such things. Moreover, we assume that the agent's actions have stochastic effects. So the agent, it knows what it can do. It knows what can possibly happen if it does these things. It knows the probabilities, perhaps, of things happening when it does these things, but it doesn't know exactly what will happen before it executes a particular action. Okay, moreover, what we want to reason about is a sequential decision-making process here. Okay, where we are assuming that the agent is not myopic, is not just interested in the very next action, but is trying to come up with a sequence of actions or a policy to execute, and is interested in optimizing some quality of this action sequence in some way. Regarding sensing, in this talk, we're going to assume that the agent's sensing is perfect. So the agent's sensors have no noise and give it perfect information about what it's trying to sense. Now, this is not a universal assumption that's made in planning under uncertainty. There are models there that can operate under the assumption that the sensing is imperfect, right? But the advantage of assuming that it is perfect is it still lets us model many real-life scenarios and makes our models more tractable. We also assume that the environment is fully observable to the agent. So not only are agent sensing perfect, but also the agent can get to know everything there is to know about the environment. Again, there are so-called partially observable Markov decision processes, which also fall under planning under uncertainty, that don't make this assumption. And I'll briefly talk about them as well. But the advantage of making this assumption is, again, it makes our models more tractable. Okay, so what's the main question in planning under uncertainty? Well, what we're interested in is giving the agent the tools to optimize the sequence of actions that it's choosing in this dynamic environment according to some measure. So if the agent is trying to get to the goal, the agent might want to try to optimize the amount of time it takes it to get to the goal, the cost of getting to the goal, and so on. All right? What problems can we solve under these assumptions? Here are a few, just a few. One, which is actually currently being worked on at NASA, is trying to land damaged aircraft. The idea here is to help the pilot to land an aircraft that has been damaged or has sustained some system failures to land safely in the presence of uncertainty about what the aircraft can do, about the weather at the nearby airports and around the aircraft, and so on. For something completely different, crowdsourcing. By the way, here, typically people don't assume full observability. Here, people model it with MDPs. So in crowdsourcing, you typically have some tasks, and the tasks can be wildly different from transcribing audio records to classification tasks. And what you want to, and you have a pool essentially of workers that are not particularly skilled at anything except for what humans are naturally skilled at. And what you want to do is break up your large task into small tasks so that you can then recombine the results of the work of these human agents into a good high-quality result. So one example, something that's actually being worked on here at Microsoft, is optimizing the classification tasks, the galaxy classification task on the citizen science project called Galaxy Zoo. Okay, here you want these workers to classify galaxies for you based on the galaxy's images, and you want to try to have the classification results that are as accurate as possible while hiring as few workers as you can. Again, for something completely different, and this is a project, by the way, that I was personally involved in during my internship here at MSR, is scheduling operating system updates. Okay, the idea here is that there is some default way of scheduling updates. Essentially, by default in Windows, they're downloaded like something like 4 a.m., which is unsatisfactory in many senses. For instance, you don't. If the user has started some important job to run overnight, you don't want the computer to just download updates and restart the machine in the middle of that important job. So the question here is, how do we schedule OS updates in a timely manner before their deadlines, but at the same time without interfering with the user? Okay, otherwise the user will look like this. Okay. Now, as any research field, a live research field, planning our uncertainty has challenges. Right? Life would be very boring without them. And the first one is, as in many other areas of AI, is the curse of dimensionality. Right? As we will see, the standard methods for coming up with policies under uncertainty essentially try to reason about states, most or all states of the environment, all possible states of the environment. And obviously, that doesn't scale too well. So how do we as humans handle these problems? I mean, we can handle pretty large problems of planning under uncertainty. Well, we reason about the problem structure. We recognize some patterns about the world, and we try to reason about the world in terms of these patterns. And in the work that I'm going to show you, I'm building methods that essentially try to do that as well. Try to reason about patterns, the patterns of the problem. The second issue is that even the models that we can solve, not very efficiently at this point, they're still too restrictive for many real problems. All right? They don't give us a theoretical, principled way of reasoning about things like dead ends, for instance. Well, up till recently, they haven't let us do that. So what we need is more general models, but also efficient algorithms for solving them, because really just the more expressive models, if we can't solve them, don't do any good for us. And again, that's the challenge that I'm going to talk briefly about at the end of the talk. Okay, so here's the outline for the rest of the presentation. First, I'm going to give you a brief overview of Markov decision processes, and then explain how we can deal with curse of dimensionality by coming up with these methods that extract problem-specific structure in an automatic, problem-independent way and use the structure to solve planning problems. All right, as a result of reasoning about structure, these methods are efficient, as I'm going to demonstrate. Next, I'm going to talk about extending the existing models. I'll briefly, again, talk about why we need to do this, why this is difficult, and the recent progress in this area, and finally conclude about talking about things that I'd like to do moving forward. Okay, so first, a brief intro to Markov decision processes. Right, this is if you assume full observability, this is really the primary way of modeling planning scenarios. And to introduce it, and also the algorithms further down the talk, I'm going to be using a small toy problem example, essentially. Now, don't be deluded by the simplicity of the planning, this example, because the methods that I'll show you are actually capable of dealing with something much bigger in series. So here is the example. Okay, we're going to model a rational agent, a gremlin, that's trying to sabotage an airplane. Okay, now gremlins are apparently these creatures whose sole purpose in life is to sabotage airplanes. Right, that's what Wikipedia says in any case. To achieve its objective, the gremlin will need some tools first, and then I'll explain how using these tools that it can pick up, it can actually sabotage the airplane. So, formally speaking, an MDP is this tuple consisting of several components that try to describe various aspects of the problem you're trying to model. And the first of them is a set of state variables. So the variables that are somehow relevant to describing the state of the environment. In our example, we're going to have 5 of them. We're going to assume that they're binary. We're going to have a variable for whether the gremlin is alive or dead. The objective of the gremlin will be to sabotage the airplane while actually not dying. We're going to have a variable for whether the airplane is intact and for whether the gremlin is holding 3 tools, the wrench, screwdriver, and the hammer. Okay? Now, the set of variables implicitly induces a state space. Okay, now a state space really is just a set of vectors that are conjunctions of these variables' values. Okay? By the way, in the rest of the talk, I'm going to refer to an assignment of a value to a variable as a literal. It's like a literal in logic, except you can have more values than just true or false.
The states are binary?
So in this example, yes, but in general, they can be just discrete values or even continuous. We'll have initial state. We'll assume that we know the initial state, although we really technically don't have to assume this. In this case, the initial state is the gremlin is alive, the airplane is intact, and the gremlin is not holding any of the tools. All right? And then we'll have a set of goal states. States where the agent is ultimately trying to get, which in this case is any state in which this conjunction of literals holds. Okay? The gremlin wants to be alive, wants the airplane to be sabotaged. Okay, now on to the actions, on to what the agent can actually do. In this sort of description, you give actions by specifying templates, each of which has two essentially important components. And the first component is preconditions. Okay, precondition, again, it's a conjunction of literals that tells you in which states the agent can use this action. So essentially, the agent can use these actions wherever this conjunctions of literals, these ones, wherever they hold. So the gremlin can pick up a wrench if it's not holding the wrench already and is alive. Yeah. The second component is what can happen when you execute these actions, the action's effects. Again, these are conjunctions of literals that tell you where you transition, where the agent transitions, if it executes the corresponding actions. In this case, in the case of these actions, the gremlin typically ends up with the tool in its paws, right? Except when it's trying to pick up a hammer, the hammer is large, the gremlin is small, so it may fumble and drop the hammer. Okay, that's one possible outcome of the action. And the other possible outcome is that it succeeds in picking up the hammer. Okay, so this is the set of actions. This is the set A in the MDP tuple. T is a transition function that tells you with what probability the corresponding effects can happen. In deterministic actions, essentially like picking up a screwdriver or a wrench, it assigns the probability of 1 to the corresponding transition. And in case you have several effects, well, it assigns the probability to every possible transition. Okay? Just to
Do you really need the notion of preconditions, or can't you just think of it as a giant three-dimensional matrix that tells you the probability of going from one state to another state on taking an action?
You absolutely can, but specifying it in this form lets you convey the structure of the problem to the planner, okay, which is very useful. But yes, indeed, in many formulations, you don't assume that you even have preconditions. So again, to complete the example, once the gremlin picks up the tools, it can use them to actually sabotage the airplane. It can use the screwdriver and a wrench to unscrew a few bolts and make the airplane dysfunctional. Or it can strike the airplane with a hammer a few times and damage it this way. But the possible unfortunate consequence of this action is that the fuel vapors detonate, the airplane blows up, and the ground dies in the process. Right? A final component of the MDP specification are costs. It's a cost function that essentially tells you how much it costs to execute an action in any given state. In this problem, we're going to assume that all costs are just 1, okay, for simplicity. Now, given this MDP description, what do we ultimately want? We want a specification of behavior for the agent to follow in any state of the world. All right? And preferably, we want this behavior to optimize some objective, like minimizing the expected cost of getting to the goal. Right? So a formal description of this behavior is a policy, which is a mapping. In this case, we're going to consider mappings from states to actions. OK. Now, how do we solve this beast? All right? The standard methods follow the following general kind of approach. They compute the value function. And the optimal value function is really something that tells you what's the optimal cost, expected cost, of getting to the goal from any state. Okay? As it turns out, this is at least conceptually very easy to compute. All right? And once you have that, as it turns out, it's very easy to derive the optimal policy from a pi star. Again, the details don't really matter. The important point is that this is very easy once you have the optimal cost to go. And you can kind of already see why these approaches fail to scale. Right? The number of states in your environment is exponential in the size of the MDP description, in the number of state variables. Right? So you can't really scale too far. And the thing is, if you want the optimal value function, right? This is really as well as you can do if your variables are discrete, right? Some functions are not really representable exactly by anything other than a table, right? So if you want the optimal value function, you're kind of stuck with these methods. And that's exactly what methods like value iteration, policy iteration belongs here as well, RGDP, and so on do. Okay, they try to compute this optimal cost vector and fail to scale. So ultimately, the only thing you can do if you want to solve big problems is really you need to approximate. You need to sacrifice some aspect of the solution quality and get an approximate solution. And there have been two major paradigms for how to do that in solving MDPs. The first one is called determinization, and as its name implies, essentially it consists in relaxing your probabilistic planning problem by throwing away all the uncertainty about actions effects. I'll show you one way to do this. So what this achieves is, it turns the probabilistic planning problem into a deterministic one. Now, why would you want to do this? As it turns out, classical planners, the deterministic planners, the ones that solve this kind of problems, they're really, really fast. Okay? They're much more scalable than state-of-the-art in probabilistic planning. So as a result, what you can do is the following. If you don't care about computing the policy for the entire state space, if you just want to plan as you go, plan online, what you can say is, so I'm in this state, right? I want to select an action. I'm going to determinize my problem, and I'm going to pass it to the classical planner. I'm going to ask it, give me a few plans from the state where I am to the goal in this determinized version of the problem, right? It does this very quickly, and then based on the, say, action statistics over the plans that it gives you, you somehow select the action that you want to perform in the current state.
So it's a greedy algorithm?
I mean, you can view it as greedy. It's just very, very crude. Okay, that's the way to view it. Yeah?
So you assume the transition probabilities are fully known?
Yes, in this setting we do. Yes, although again later on I'll talk about what to do when they're not, or you can't really tractably use them.
But determinization means from any state on any action you get to just one other state, right?
Exactly.
Yeah. Exactly.
So you know, if an action has a catastrophic effect, you're not taking this into account when you're doing this, and that's exactly the weakness of this approach. And if you do it this blindly, you're going to have problems with dealing with actions that have catastrophic consequences, or simply, as a side effect, set you on a very expensive path to the goal. Yeah.
People tried to do like multiple samplings to do different determinizations where you said instead of...
Brilliant, exactly. People have tried improving on this. Okay. There are approaches that this is kind of just the general idea. People have tried to improve it, but even in those approaches, you lose something. Like if you do multiple samplings, for instance, well, the method becomes much more expensive because you have to solve many more problems for each state you're in. Okay. Now the other kind of general kind of class of approaches that people have been using is function approximation. Really, it's the kind of dimensionality reduction that is probably familiar to many of you from machine learning. The idea here is that these methods that I've described, they really solve a problem in the number of parameters equal to the size of the state space, right? They learn the value function, right? It has number of parameters equal to the size of the state space. So the idea here is to pick a few basis functions, okay? Just only a few. And each basis function can be viewed as giving you some information about possible value of possible optimal value of the state. Okay, and then you approximate the optimal value function somehow with a combination of the basis function. For instance, by taking a linear combination of them. So the only parameters that you need to learn here are these weights. Okay, and if there are a few basis functions, there are only a few weights. Now the problem with these approaches, especially in domains with discrete variables where you can't put any kind of natural metric on the state space, is that to get meaningful results, you need to have a human engineer look at the problem and figure out what are the meaningful sort of meta features of the problem, okay, and encode them in the set of basis functions. So here we have these two kinds of paradigms with their own serious disadvantages. One is not so good at dealing with probabilities, with uncertainty. The other one involves a human in the loop. And what the work that I've done achieves is it marries these two approaches to get rid of the cons of both of them, essentially, and to come up with something that can reason about problem structure encoded in basis functions in a problem-independent way, by extracting basis functions in a problem-independent way, and because of that, scale to much larger problems, and perform better than either of these approaches. All right? And what I'm going to show you next is how this is actually done. All right? But before we get into details, I'd like you to think about how we as humans reason about planning problems. Right? So most of you buy the fact that we try to reason about properties of states. But how? Okay, so suppose you need to go grocery shopping, right? And suppose that your car just doesn't have enough gas to get, say, to Costco. Okay? Now, in a sense, the state of the world isn't so good, right? Because getting to the shop is kind of expensive. First, you need to get to the gas station, then you need to, pay for the fuel and so on, right? So what you want to do is you want to go to a cheaper state, a state that's better, where your car does have gas, okay? So the way we reason about states of the environment is, if we're in a bad state, if the properties of the state would tell us that the state is bad, we want to go to a better one, okay? And that's essentially what these methods are attempting to achieve. In particular, the question is, well, what are the good properties of the states? What are things that tell us good things about states, and what are things that tell us bad things about states? So in this work, we've considered these properties that take the form of conjunctions of literals, like the one in pink here, where the gremlin is alive, the airplane is intact, and the gremlin is holding the hammer. And as it turns out, and we restrict ourselves to properties that have a very, very particular meaning. Okay? We want conjunctions of literals such that if such a conjunction of literals holds in a state, here are 3 states where that conjunction of literals holds, okay, we want the guarantee that we can reach the goal via some sequence of actions from any of these states. Okay? So intuitively, these properties, these conjunctions of literals describing these properties, are good in the sense that they tell us that you can reach the goal. There's a possibility you will be able to reach the goal from any of these states. All right? And since we ultimately want to turn these properties into basis functions, with each of them, well, we're going to associate a value, essentially. The basis function is going to say that it's going to have value 1 in any state where such a property holds, okay, and a value 0 otherwise. So for each such property, we'll have a basis function.
And what is reachable, if even reachable with a positive probability?
Yeah, possible, not for certain, but with a positive probability. Yes. Yeah.
The causal cost that you have to get to the goal may exceed the benefit when you reach your goal in some settings, because it's just taking so long for me to get my goal state. That path is actually undesirable.
Exactly.
But here I'm labeling it as a good state.
Well, they're good only in an intuitive sense. Well, in a moment I'm going to explain how we can actually distinguish between these good properties even by assigning weights to them that are going to tell us that this property is really good in the sense that we can reach the goal in a very cheap way, and this other property is it's good in the sense that we can reach the goal, but it's not so good in the sense that reaching the goal is expensive. Okay? But for now, this is the general form of the properties that we want to use. Now, of course, we also want to know what makes a state bad. Right? We want to know from which states reaching the goal is, say, impossible. Right? And for that, we'll have a separate kind of properties. We'll call them no-good properties. Also, conjunctions of literals. In this case, we'll have a singleton conjunction when the gremlin is dead. And again, for these properties, we want to guarantee that if a state has such a property, here are 3 states that have this property, we cannot reach the goal with any kind of possible probability. All right? In this case, it's sort of easy to see the no-good properties as the ultimate causes of what makes a state bad. All right? Here, when the gremlin is dead, obviously you can't do anything. Okay? And again, we're going to associate with each of them a basis function that's going to have a value of infinity if the property is present in a state, and then 0 otherwise. Okay. Now, that's fine. We know what properties we want. How do we actually get them in an efficient way? Remember, that was sort of the weakness of dimensionality reduction approaches, in that you needed a human to come up with the basis functions. Okay. It turns out we can come up with both of these kinds of basis functions that I've described automatically. And here is how we come up with the good properties. Okay? That's exactly where the classical planning paradigm comes in. What we do is we turn the problem into a deterministic version. All right? Multiple ways of doing this. We're going to follow the most straightforward one, which is you take each probabilistic action, you split it into one deterministic action per effect. Okay? So in the case of this action, we're going to have one action which helps the gremlin achieve the goal for certain, and one under which the gremlin just for certain dies. All right? As you may imagine, this action is pretty darn useless. Now, how do we actually extract them from the properties from this classical planning problem? What we do is we pass this problem to a deterministic planner. Okay, the same way as planners like FF-replan do under the classical under the determinization paradigm, and we're going to ask the deterministic planner to find for us a plan to the goal from the state that we're interested in evaluating. All right, so if we pass it the initial state, it's going to come up with something like this, just a linear plan to the goal. Gremlin picks up the hammer and strikes the airplane. All right, and what we're going to do afterwards, that's actually the key step in the process, is we're going to regress this plan. Now, if you know what regression is in machine learning, that's not it. What this regression does is it essentially takes the conjunction which characterizes the goal, and it's trying to figure out what did you need, which of these literals did you need at the previous step at the last step in the plan to achieve the goal from the last step. So what did you need to execute this action in the state? Formally, what it does is it takes the goal conjunction, removes from it the effects of the last action, and adds the preconditions of the last action. All right? So if you do this process to the last action in this plan, what you arrive is, well, it's just the precondition of this action. That should be sort of pretty obvious. At the previous step, the gremlin must be alive, the airplane must be intact, and must be holding a hammer. Okay? You continue the regression. You roll back the next action by treating this conjunction as a sub-goal, in a sense. And what you arrive is, well, at the previous state, to execute this action in brown, the gremlin must have been alive, the airplane must have been intact, and the gremlin must not have been holding the hammer already. All right? Now notice, these conjunctions of literals do have the guarantee that we want. If you have such a conjunction of literals in a state, you know that you can reach the goal via the suffix that you regressed to obtain this conjunction of literals. Right? In other words, these conjunctions of literals are exactly the properties that we want, and extracting them in this way lets us get the good basis functions. Right? Moreover, remember, we will ultimately want to learn weights for these basis functions. And just as initialization, we're going to give each basis function the weight that corresponds to the cost of the plan that we used to regress to obtain it. Okay, in this case, all actions have a cost of 1. So this basis function gets a weight of 1, and here this one gets a weight of 2. So intuitively, in our setting, the lower the weight, the better the basis function is supposed to look.
If I got it right, in the previous slide or two, what you did was determinize the problem by taking each action and creating 2 actions, one where it had effect A and the other where it had effect B, but not paying attention to the probabilities of those 2 things. So could that cause problems in the second step if you end up basing a plan or deciding on good states because something looked good in this deterministic version, but actually it's extremely improbable?
So again, for now we just extracted these good states. Now we're actually going to learn the weights of these states, and that's where this probabilistic information that we've discarded.
Well, put differently, could you miss some good states? Like, you might not find all the good states here, right?
Well, no, typically if a classical planner gives you, does manage to find the plan, which is pretty much always if such a plan exists.
But there may be many, many plans.
Yeah, sure, but it will give you some.
But what if it doesn't give you ones that correspond to actually likely outcomes because you ignored the probability?
So one answer to this question is you're going to miss out on something, but the other answer is there are several ways of doing this determinization, and one way in particular is to essentially when you do the conversion, when you split the actions, you modify the costs of these outcomes by dividing them by the probabilities, for instance. So essentially, outcomes that are expensive or have low probability, or both, they're going to look like really expensive actions in the deterministic version of the problem. Yeah. Again, that's a possibility, and you can easily plug this into this method. Yeah, please.
So turning into this randomized strategy into a kind of deterministic, I'm wondering if there will be cause the problem that the number of basis function will be exponentially large.
Exactly. So in fact, if you notice in principle, there could be the number of basis functions could be 3 to the power x, where x is the number of variables. Yeah. In fact, in theory, there could be many more basis functions than there are states. Yeah. But the number of meaningful ones is typically very small. That's one thing. And the other one is that, as you'll see, we'll get basis functions on demand. So we'll only get them as necessary. And the nice thing about each of them is that once you get a basis function, you typically can evaluate a whole bunch of states. So you don't really need more basis functions for a whole bunch of states. And that's essentially what's going to keep the number of basis functions under control. Yeah.
So when you're showing the determinization, right? So you're showing it for one action.
Yeah.
Like, do you determinize like the entire chain? Like, is that sort of exponentially in the length of the chain? Like when you have chained actions, or how does it?
Well, no, because so our actions are not chained. So given a description of an action with precondition and an effect, for each such template, so to say, you split it in 2.
I see. So you look at each of them separately.
At each action separately, exactly. So you don't get exponential blow up. This process is essentially linear in the number of actions or actions outcomes. If you want.
I'm just sort of curious where this is going.
Yeah.
So the original algorithm is guaranteed to find the optimal answer in exponential time.
Yeah.
When you're done with this, will there be another time trade-off, a time quality trade-off that you can guarantee?
So in terms of guarantees, no. We just tell you straight away. It works well in practice. Well, empirically, we've done a lot of tests compared to other methods. It produces better results than other approximate methods. It works faster than them, uses less memory. But other than that, I mean, other than empirical guarantees, you can't really say much.
And does anything have any guarantees?
Typically not. So there are some dimensionality. When you're doing approximations, if you want it to be efficient, essentially, you should be prepared to lose out on guarantees. There are some methods, dimensionality reduction methods, that say that if this method holds, if it ever terminates, then you have some guarantees. Yeah.
There is some notion of, the notion of good is not that absolute, because you could imagine a problem in which every action can have every possible outcome with a very low probability.
Mm-hmm.
So if you have this, everything is good.
Yes.
Except that they're going to have high cost if you do this division effect. So,
yes.
So you're not only looking for good combination of literals, but good with reasonable cost.
Yes, yes.
So it's not just good and bad, it's more subtle.
Exactly. So when we're learning the weights, we're going to get, part of this,
You could have a situation where all the states are good, because there is a path that has very low probability.
Yeah, so in goal-oriented settings, you typically don't really have that. Okay, but we are going to look later on in reward-based settings where this is often the case. Okay, no state looks particularly bad or good. Okay, in terms of the long-term reward that you're getting. And again, for those approaches, for those problems, they're kind of a corner case for this class of approaches, and for them you need something different. Okay, and I'm going to briefly talk about that later. All right, so let's move on. Right, so now about the meaning of the basis function weights. As many of you have already pointed out, properties are not just good or bad. If they're bad, they're kind of, at least in the sense that we described, they're really bad. Okay, you just can't reach the goal. But if they're good, you may be able to reach the goal via essentially different costs depending on what the basis function tells you. So here's one example. Here's the state that has one basis function, one property in blue, which essentially guarantees that you may be able to, in fact, in this case, that you definitely can reach the goal via this two-step plan, right? And then there is this basis function in pink that essentially was obtained by regressing a one-step plan where the gremlin just hits the airplane with a hammer, right? But indeed, if you try to execute this plan in the probabilistic world, there is a danger that the agent will actually die, right? So intuitively speaking, what we want to do is learn basis functions weights in such a way that basis functions like the one in pink look worse than like the basis functions in blue. All right? And so the details of how to do it are sort of slightly messy. So I'm not going to concentrate on them, but I'm going to show you how the process of extracting the basis functions and learning their weights can be put together to produce a planner. Okay, and the planner is called the Retrace, which stands for regressing trajectories for approximate state evaluation. So here's how it works. You're given a problem. Probabilistic planning problem model is an MDP. The first thing you do is you determinize it. All right, you're going to just cache the determinized version of the problem and never do the determinization process again. And you're going to cache it in this thing called the extraction module that's going to handle basis function extraction and weight learning for us. And then what you do is you run a state space exploration routine. Intuitively speaking, what it does is it analyzes various states in the state space in some order. Again, the order doesn't matter. Looks at their values and sees which states are good in the sense that the values of which states are high, and trying to determine the policy and the best action to do in these states. All right? But of course, so it needs to have values of these states. And at the beginning, when the process just starts, remember, our tool for evaluating states is basis functions, and we have no basis functions, right? So the state space exploration routine runs into a state, realizes it has no basis functions for it, and asks the extraction module, can you evaluate this for me? All right? The extraction module runs a classical planner from that state in the determinized version of the problem, as I just described, regresses the plan that it gets, okay? Extracts basis functions via regression. And you remember, if you start a plan in some state and then you regress it, you definitely get at least one basis function, that is one property of the state where you started, right? So you have some information to evaluate the state. So the extraction module evaluates the state and passes the value back to the state space exploration routine. Now the state space exploration routine does some more analysis and tells the extraction routine, hey, what you need to do is you need to update the weights of the basis functions that you use to evaluate the state in a certain way. So to correspond with our intuition that bad basis functions should get high weights and good ones should get low weights. Okay, and essentially that's how the process operates, right? The one thing to notice is that at the beginning, when state space exploration just starts, for the first few states, you'll need to run, you essentially need to evaluate, you'll need to extract new basis functions to evaluate these states. But as the number of basis functions that the extraction module already knows about grows, right, it's growing increasingly able to evaluate states that it's passed via the basis functions that it already has. Okay? And again, that's what controls the number of basis functions. You get them sort of on demand, and demand for new basis functions is shrinking as you go along because you know, intuitively speaking, more and more properties of states. Now, what I've swept under the rug so far is that you may run into states that are dead ends, from which there is no path to the goal. So the classical plan is simply just going to fail on you. All right? And again, when the state space exploration process starts, it's, you know, you'll have to run the classical plan on a few such states and memorize a few dead ends. But at some point, remember, we have this other kind of properties called no-good properties. And no-good properties essentially help us identify dead ends. So at some point, the extraction module invokes this machine learning procedure called sixth sense, which helps the planner sense dead ends, right? And this machine learning procedure essentially uses two kinds of training data. You can view it as positive examples and negative examples. The positive examples are dead ends. Those are the states that you want to classify, well, as bad. And basis functions are training examples that summarize the good states, those that you want to classify as, you know, not bad, using the no-goods. All right? Again, once you invoke this procedure a few times, you'll have a few no-goods. And with the help of these no-goods, you'll be able to evaluate states without running classical planner from them, but in a very cheap way, using the basis functions. And by running this process after some time and terminating it, you get a policy. Now, the last piece of the puzzle that I haven't showed you yet is how to actually get the no-goods. How does sixth sense operate? And that's what's coming up next. So the main idea, so first of all, sixth sense is you can be used as a two-stage algorithm. Okay, in the first stage is going to generate conjunctions of literals that could be no-goods, like no-good candidates. And then it's going to test each of them. And what's going to drive the generation of no-good candidates is the following observation. So notice that basis functions and no-goods, the good properties of states and bad properties of states, they give us exactly opposite guarantees about the states in which they hold. A no-good says you can't reach the goal under any circumstances, and a good property says you can reach the goal somehow. Okay? Since both of them are conjunctions of literals, a no-good and the basis function can't coexist in one state. Right? Well, this means that these conjunctions of literals must somehow clash. They must contradict each other in some way. So essentially, a no-good can be viewed as a conjunction of literals that for every basis function in existence contains a negation of some literal in that basis function. Right? Now, we don't know all the basis functions. Right? We don't know all the basis functions in existence. And we don't even want to know them because, again, there are many of them, as you pointed out. So what we're going to do is, given the basis functions that we do know, we're going to essentially compile a set of literals that contradicts every basis function that we know. In particular, there is really only one minimal no-good in our problem. That's when the gremlin is dead. And notice that it contains, well, it consists of just one literal. And this literal is a negation of some literal in every basis function that we know. If these are the two basis functions that we know, it contradicts this basis function and this basis function, because in both of them say that gremlin must be alive. All right. So what we're going to essentially do is we're going to go through the basis functions that we have and sample contradicting literal for each of them, and that's going to form our no-good candidate. Now, of course, since we don't know all the basis functions, we don't know if the set of literals that we've compiled actually defeats every single one of them, every single one in existence. Yeah. So we'll need to test whether this no-good candidate is indeed a no-good. Okay, and we're going to do this with a procedure that's polynomial the number of MDP variables, not states, but variables, and sound. Okay, I'm not going to go into details. I'll just say a few words about it. But first, let's look at how we generate the candidate. Okay, remember, besides the basis functions that are partly going to drive the process of creating a no-good, we also have dead ends that we've seen. Yeah. And dead ends, intuitively, if we look at the literal occurrence statistics in them, they help us identify the literals that are somehow, intuitively speaking, are likely to be part of a no-good. Right? If we look at the literal occurrence statistics, we see, for instance, that this literal that actually forms the only no-good that we have in the problem is quite common among them. Right? It occurs in every single dead end. Of course, the literal occurrence statistics may be correlated, and there are other literals that are also popular in dead ends, right? So using these statistics, we can make the process of sampling a candidate more efficient by, for a very basis function that we have, picking a set of literals that defeat it, okay, that we've already been through that part, looking at their occurrence statistics in the dead ends, and sampling a literal from this distribution induced by the literal occurrence in dead ends. Okay, so if we do this, in this case we roll the dice and sample from this distribution in red, and say we select the literal that says that the gremlin is holding a hammer. Okay, now we go on to the next basis function that we know about, say this one. Okay, and we do the same thing, right? We'll look at the literals that contradict this basis function. We'll look at the occurrence statistics in dead ends. We sample from that distribution and say we select this literal that says that the gremlin is dead. Now, if the two basis functions that I've just shown you is all we know at the time we run this algorithm, then we stop here. Okay, we've just finished creating our candidate. All right, and at this point we test it. Okay, now there's this procedure called planning graph, which some of you may know, but I don't want to go into details of it. The important part is that you can actually use it. You can modify it significantly to perform the following test. You take a no-good and you see if you must fail to reach the goal from every single state where this no-good holds. Okay, except if you do it just the way I just described, right? This is going to be very expensive, right? Because there are many states in which no-good applies. There are some tricks in which you can essentially lump all these states in which no-good holds into one, and do a test using planning graph from that accumulated mega state, you would say. And the result is the resulting procedure that you get is polynomial, so it's very efficient in a number of domain variables. It's also sound, so if it tells you that you can't reach the goal from any of the states where the no-good holds, you should believe it. Okay. Now, where does the trick come from? It's incomplete. Okay, so there may be conjunctions of literals that are indeed no-goods, so conjunctions of literals that have the property that you can't reach the goal from any of the states in which they hold, but this procedure won't tell you that. Okay, but in practice, again, it's quite effective. Now, the last step in the process is notice that the no-good candidate, by the way, for this no-good candidate, this procedure is going to say that yes, it is indeed a no-good. But this no-good is not minimal in the sense that it contains information that doesn't really is superfluous, right? We don't really care if the gremlin is dead and clenching the hammer in its dead paws, right? It's irrelevant. What really matters is that the gremlin is dead. And to reduce this no-good candidate further, we essentially remove literals from it one by one and redo the testing. Okay? And in this case, we get a no-good that's minimal in some sense, in the sense that you can't reduce it any further. Okay, and that's essentially, that completes the description of Retrace and its component sixth sense. And the result is a planning algorithm that essentially outperforms state-of-the-art in goal-oriented problem solving. We tested on 90 benchmarks. The probabilistic planning community has a whole bunch of benchmarks, like the machine learning community. And across them, our method essentially beat the previous state-of-the-art. Here's one example, an example on 15 problems from a single set. Here, problems roughly increase in difficulty and size from 1st to the 15th. And in particular, these last 3 problems have state space equal to the 800th states. Okay, so the number of particles in the universe doesn't even begin to describe this number. It's this huge. Now, of course, these problems are structured, right? And the strength of our approach is in being able to extract this structure and reason about it in an effective way to come up with good solutions. So in particular, we compared it to one of the state-of-the-art algorithms that we compared to is called the FF plan that I mentioned before. As already said, so these methods do have problems with dead-end states. Okay, if you determinize the problem, as FF plan does, and just completely throw away the probabilities, well, you're going to run into bad situations from time to time. However, the advantage is that this kind of approaches is it's very efficient because really it's just the classical planner running all the time, and the classical planners are really efficient. Yeah.
Does FF plan reweight the paths in the way that? Oh, sorry, it's not doing the split the way that you're doing, so it doesn't have an opportunity to do like costing.
No. I mean, you could slightly improve its properties by essentially doing this cost weighting that I described. And yeah.
I'm curious if you like, have you tried that of just taking the first part of what you described, where you split every action, did the cost reweighting, and then just ran a deterministic planner on that to see how that would compare with your full method?
Yes. So the caveat here is that if you can solve the problem this way, it works better. The caveat here is that up till recently, deterministic planners, they essentially could only efficiently handle uniform action costs.
I see.
Okay? So if there was action costs were different, they wouldn't be so fast, and you kind of lose one of the big advantages. The situation has improved since then, but yeah. In any case, so this planner can actually scale to the problems of this size as well. A free plan can scale. However, as you see, in problems where an optimal policy exists, an optimal policy, in this case, by the way, we're measuring the quality of the output in terms of how likely the policy is to reach the goal. Okay, and this is done just by simulation. So in these cases where there is an optimal policy that reaches the goal with 100% probability, but there are dead ends, if a free plan does quite poorly. You see, it runs into problems due to discarding uncertainty. There is another planner called FPG that does a more principled decision theoretic analysis. And as you see, generally on problems where you can reach the goal with high probability, it comes up with optimal policies in that, according to that optimization criterion. But the consequence of doing this, the kind of reasoning that it does, is that on large problems, it fails to scale. It just fails to solve them, fails there completely. Okay, and Retrace essentially beats both of them by a significant margin in terms of policy quality across a range of problems. The other kind of experiment that we did is, well, how well does it scale compared to optimal or near optimal planning techniques? A very famous, at least in probabilistic planning community, optimal and relatively efficient algorithm is LRTDP. It's a heuristic search algorithm, so if you run it with an admissible heuristic, it's going to give you an optimal solution. If you run it with an inadmissible heuristic, it's going to give you it's going to be more efficient, but it's going to give you a suboptimal solution, but typically not too bad. So here we plotted the amount of memory that these three techniques use on the y-axis on the log scale, and notice that LRTDP in both cases, whichever heuristic it uses, it's linear on this log scale. So really, it scales exponentially with the size of the problem. Okay, and Retrace, essentially, its graph is much closer to logarithmic. So it scales polynomially, maybe even linearly in the cases of these particular problems. Not always, of course, in the size of the problem. Okay. Just a brief mention of the fact that you can actually use the techniques, this reasoning about basis functions that I've described, to also help the existing techniques. Okay, you can use the initialization values of basis functions. You remember when we regressed the plans to get the basis functions, we got some weights for them. You can use these weights as heuristic values, essentially, to help heuristic search planners. And what you do is, well, you simply run a heuristic search planner like LRTDP, and you feed to it the value estimates based on the initial weights of the basis functions. Okay. The result is this heuristic that we call GOTH, generalization of trajectories heuristic. And empirically, again, we ran LRTDP with this heuristic and with the previous heuristic known to be kind of the most informative on this whole range of problems. And what we've discovered is that GOTH empirically typically leads the planner to explore many fewer states and at the same time have comparative or better policy quality than if the planner uses that other efficient, pretty informative heuristic called HFF. Okay, so here you can see that GOTH essentially leads the planner to use less states, less memory. Okay, dots below the diagonal denote less memory. All right. So yeah.
I'm wondering, it seems like the success of this approach really depends on discovering those basis functions.
Yeah.
I'm wondering, are there settings where discovering those basis functions are harder than others? For example, when you tested on these 90 different domains, when the variables you have in your state representation have complex dependencies, is it getting harder to discover those basis functions or not? Like any
So,
experience you had with those?
I don't know of cases where it's harder to discover basis functions. So this range of this set of problems that we tested on, I mean, the problems there are synthetic, but they are structurally complex, and they're structurally complex in different ways. So the one possible kind of scenario where this approach might not do so well is the one that you hinted at, where you essentially have each action just has a ton and ton and ton of effects, right? So determinizing such actions is very expensive. Solving such determinized problems would be very expensive, and also, it's hard to select good basis functions in those cases. But see, such scenarios are fairly rare in goal-oriented settings. They are in reward-oriented settings, but in goal-oriented settings, they're rare because if an action has a ton of effects, right, and you want to reach the goal, well, the chances are one of these actions leads just directly to the goal. So the problem becomes, in a sense, simple. Simple in this way. But yeah, other than that, I don't really know of really bad scenarios for this.
You could encrypt the variables by replacing them by random XORs.
Okay.
Existing variables until you have a code that really encrypts them in a nasty way, and the structure is no longer apparent, no longer appear clearly.
So you're suggesting
you take a subset of the variables, random, you compute the XOR. So that's a new variable.
Okay.
Another one, random, you compute an XOR. And then you compute a set of new variables that represent all the information in the initial variables. So it's kind of encryption. You have encrypted the structure of the variables behind some random XORs. So now it's going to be quite difficult to find any subset, any basis function which is a subset of variable now corresponds to the whole set.
So yeah, I mean, if you start trying to build scenarios adversarially, I mean, sure. They exist. Yeah. I mean, definitely, it's just a matter of like, do they seem to occur in practice? And I mean, that doesn't seem to be the case. But yes, indeed, you can construct such problems. Okay, so the approaches that we've considered so far sort of assume that you do have a goal, but the agent is actually trying to achieve a goal. But in some scenarios, like in portfolio management, you don't have a particular goal. You just want to, well, manage the portfolio and keep earning money, well, as long as you can, sort of. So the processes here are essentially reward-oriented. You want to get good long-term reward, which is the same as maximizing long-term reward is like maximizing minus cost. And that's actually a subtle optimization criterion, because when you cared about reaching the goal in some sort of cost-optimal way and you had dead ends, really you had a very convenient sort of proxy optimization criterion there. Clearly, I mean, if you're in a life-and-death situation and you want to optimize cost, the first thing you care about is getting to the goal. Okay, staying alive, right? The second is optimizing for cost. Here, there isn't such a convenient proxy optimization criterion. You really kind of need to solve the reward optimization problem more or less directly. All right. So in this case, the goal-oriented basis functions of the types that we just talked about, they are less applicable. I mean, in some situations, you can identify high reward regions of the state space, turn these states in these regions into goals essentially, and do the kind of regression to obtain basis functions in this way. But in many cases, no state is particularly good or bad. Okay, the distinctions are much more subtle. So you need something completely different here, and I've done some research on what are good design principles for these kinds of scenarios. What I've discovered is, for instance, it makes much more sense here to plan online, especially if you have huge state spaces and actions with a ton of effects. Planning online doesn't always pay off in goal-oriented settings, because typically when you plan online, you need to you have very limited amount of time to figure out what to do. Which means typically you look up to a limited look ahead. Right? In goal-oriented settings, this may really bite you, because if you don't see the goal, if you don't have enough time to see far enough to see the goal, you can fail miserably, right? And in reward-oriented settings, this is less common. Okay, so but the two planners that came out of this research is, one of them is called Glutton. The reason it's called Glutton is essentially it momentarily eats up all the memory that you have on your machine and uses this memory for some bookkeeping tasks. It's not like it runs out of memory; it just manages it in a smart way. Okay. the main idea here is that it's planning on line, and it does reverse iterative deepening. So as long as it has time, it solves the problem for look ahead 1, 2, 3, 4, and so on. And it's based on essentially a planner that has a terminating condition, so you can always tell when it has come up with the optimal policy for a given look ahead. Okay, and when you terminate it in the middle of planning, it tells you, okay, here is the action I think you should choose, and this action is going to be optimal for this kind of look ahead. All right, we submitted it to the International Probabilistic Planning Competition. It's a kind of competition where, well, as its name implies, a bunch of planners are competing at solving a wide range of problems. It was a runner-up. It was a close runner-up. And its development, called Gourmand, actually was able to outperform the state of the art. I mean, it came out a few months later than the competition. It was able to outperform the winner of the International Probabilistic Planning Competition, which makes it state of the art in reward-oriented settings in some way. Surprisingly, so the winner of the competition was a heavily optimized version of UCT. And recently in probabilistic planning, there has been this view that if you have a problem with really complex structure, like if you have many action outcomes, right, you may know the probabilities of those outcomes, but really you can't use them in any kind of closed form computation, because you need to essentially, at every step, you need to take a summation of all the successors of each action under each state. And that's really, really expensive. So you essentially have to resort to sampling. Okay? Now UCT seems ideally suited to these scenarios because it lets you do sampling in an intelligent way. And surprisingly, this method, even though it's based on more or less of a conventional probabilistic planning technique, it actually beats this finely tuned UCT version across a range of domains. And the reason it does is in UCT, you have these parameter settings, and you really need to tune them really well for it to work. Moreover, these parameter settings are very problem dependent. So if you want to get a general problem solving tool out of UCT, the best you can hope for is, well, you just sort of pick a set of parameters that seems to work fine across a range of problems. But if you have a problem that doesn't conform to what you've tested on, again, you can fail miserably. Gourmand actually, it does have some parameters, but it optimizes them as it goes along, does it automatically, and as a result, it adapts to the problem that it's trying to solve. Okay, and because of this, even though UCT was really, really finely tuned, there were problems. There was a really wide range of problems, and across the wide range of problems, automatic parameter tuning of the kind done by Gourmand is, it's much more practical. Okay, and as I said, it doesn't need much tuning. Gives policy guarantees of some characterization of the policy quality. And if you want to play with it, I'm going to release it soon. I'm going to release the code soon. All right. So that was essentially most of the talk about the scaling up existing planning approaches. Now a few words about extending the existing models. And the first thing I have to say is that actually the previous MDP definition that I gave you was wrong. Well, it was incomplete. Let's put it this way. Actually, if you look at it, as it turns out, the cost optimizing for expected cost is an ill-defined criterion for that kind of model, and you need to restrict it to make it to make it well-defined. Okay, there are several MDP classes that you've probably heard about: finite horizon MDPs, discounted reward MDPs, and stochastic shortest paths MDPs, which are essentially attempts to restrict that previous MDP definition to make it well-formed. All right, but the cost that you pay for making them well-formed is you fail to model some scenarios that we as humans can handle. So in particular, like stochastic shortest paths MDPs, they assume that all costs are positive, which essentially means you can't have both costs and rewards in a goal-oriented process. Well, you can't model it. And it assumes that there are no dead ends. It assumes that no bad things can happen if you try to achieve the goal. All right, clearly this is unrealistic. That's one scenario where bad things do happen. If you try to land a damaged airplane, it can obviously crash. And so formally, with this model, you can't really model this. You need hacks. Okay, and so to avoid hacks, I've done some work on extending the existing MDP classes and coming up with algorithms for them. Now, first of all, why is this hard? Okay, the reason this is hard is that so in the existing MDP classes, like stochastic shortest paths MDPs or discounted reward MDPs, this optimal value function, so ultimately the solution of the MDP, can be obtained very easily by a fixed point method. So fixed point methods is called value iteration or policy iteration as well. So some examples of fixed point methods are, Newton's method, EM, and so on. Many of the commonly used methods belong to this kind, and what they do is they start with some guess of what the solution is, apply some operator to it, so improve it essentially, and then invariably converge to this unique fixed point that turns out to be the optimal solution to the problem. As it turns out, even for small extensions of the existing MDP classes, this breaks down. This operator that is used by most of the algorithms, called Bellman backup, it essentially starts having multiple fixed points, only one of which is optimal. Everything else is, isn't meaningful. All other fixed points aren't meaningful. So you somehow need to deal with these extraneous fixed points. The other observation is that in methods for solving the conventional MDP classes, we could derive the optimal policy from the optimal cost function very easily. It was a trivial, very efficient procedure. Again, even for small extensions, this ceases to be true. You can come up with an optimal value function, but if you tried to use the old way of deriving the optimal policy for it, you could get a policy, for instance, that achieves the goal with a very low probability or not at all. And then if you have a large problem, this is a big issue because, you can't really tell how good the policy is if the problem is large. Really, the only way of figuring this out is to try to execute it, perhaps in real-life circumstances. And again, that's something you don't want to do. So as recent progress in this direction, I've done some work on extending MDPs to allow a richer cost structure, so not just positive costs, for instance. And that's captured in a class called generalized stochastic shortest paths MDPs. Also, I came up with a heuristic search algorithm. So it's an optimal algorithm, but it's more efficient than, say, value iteration in the sense that it does manage to avoid visiting all the states in the state space, typically. Okay, and that work led to extension of stochastic shortest paths MDPs that let you reason about catastrophic scenarios, about dead-end states, effectively, in a decision theoretically sound way. In particular, the major extension is the one that allows you to reason about dead ends if you want to put an infinite penalty on dead ends. Okay, this is something, in fact, that even we as humans are not so good at dealing with. If we have, probabilistic, if we have an environment which is very dangerous in the sense that, reaching the goal involves a significant chance of dying, and dying to us, is like an infinite penalty, then we as humans, we often get lost. We don't really know what to do because, essentially every single thing that we do carries an inherent danger. And this extension to stochastic shortest paths MDPs, lets us do this. Lets us do this kind of reasoning. And what's something that I'm currently working on in this direction is stochastic shortest paths MDPs that allow both costs and rewards. Okay, again, we as humans actually are able to deal with these scenarios. If we have a goal, we have goals in life. We have actions that take away resources from us, like shopping. We have actions that bring resources to us, like working. And we are able to deal with scenarios like this, and current MDP classes can't. And that's the work that's aiming to fix this. All right, now a few words about what I want to do moving forward. Okay, first of all, so there is a whole bunch of applications that I'm interested in, and in particular the ones that are being worked on here at Microsoft. One of them is power management, in particular power management in computing devices. In which I'm hoping to answer questions like, when can we turn off various components, energy-hungry components of a computing device, like CPUs, screens, without interfering with the user, and at the same without interfering with user activities, so as to extend the battery life, essentially, roughly speaking. Another kind of question that also is indirectly related to this is how do we optimize the operating system so as to minimize the number of cache misses, for instance. Again, I think that's something that decision theory could help a lot with. Right now, these questions essentially are being answered by expert engineers who sit, look at the patterns in the data and try to come up with some heuristic ways of, say, evicting pages from the cache. And last summer, we did some work that essentially implies that we can do much, much better. Okay. Besides the obvious impact that it will make the devices greener. It will make the devices require more power, less energy. It will have the obvious impact that extending the battery life will make the devices more attractive to customers. Okay, it's, for instance, a deciding factor for me personally when I'm selecting between devices. And of course, that will make the Microsoft richer and Steve Ballmer more happy. So again, the key here is probabilistic planning, and planning under uncertainty, but also, of course, to take the user into account, we'll need a lot of machine learning to actually learn the patterns in user behavior. Another application, again, that's being worked at Microsoft Research and in Bing is crawling. How do you do crawling on the web in the principled way? The issue here is that there are billions of pages sitting in the index and sitting on the web, right? Some of them, many of them actually, they can change. A small fraction maybe actually does change, but many of them can change. And for some of these pages, the users really expect you to pick up the changes to these pages promptly, like changes to the news pages. And they expect you to serve the updated results as responses to queries. The issue is, well, you only have the pipeline of a certain width. You can only crawl so many pages per day, right? And the question is, how do you essentially optimize crawling so as to pick up the most important changes as quickly as possible, right? So this model can be, this scenario can be modeled as an MDP or POMDP depending on how you look at it, because intuitively what you want to do is you want to kind of balance optimization of two criteria. A, you want to get the payoff from immediate payoff from picking up new updates, but also, as it turns out, there is data about how changes in different pages are correlated. Okay, so data of the kind that tells you if this page has been updated recently, then this page has also been updated recently with some probability. So you not only want to get the immediate reward of crawling pages that have been updated, you also want to gather information about what other pages may have gotten updated. All right? And so balancing out these two optimization criteria, again, can be done with decision theory. And the huge challenge here is that, of course, if you try to model as an MDP in the most straightforward way, the branching factor, the number of actions that you can choose from, is simply enormous. Right? You need to fill the pipeline that you have, say, of width n, with some selection of pages from a much larger set m. Right? So you have, the branching factor is really, really huge. However, this problem does have lots of structure. In particular, the information gathering aspect of it may have some modularity structure. Intuitively speaking, as you select more and more pages for crawling, the amount of information about other pages that are outside that you're not actually crawling is shrinking in the sense that you get less and less added benefit from each page you add to the pipeline. Okay, and this kinds of structure actually, and the work that I've done and work that has been done on actual applications that have similar structure, essentially gives me hope that we can do something really interesting and something really efficient here. Moreover, there is another problem that I don't have in crawling that I don't really have time to talk about in detail, which is figuring out which parts of the web graph to crawl in order to pick up the new pages. So where are the new pages are most likely to appear? Again, I believe that's a job for probabilistic planning. So some other things that I'd like to work on, MDP theory. I am a firm believer that along with the practical applications of MDPs, we also need to figure out if what we're doing is sort of theoretically sound in some way, in some approximate way even. One thing I'm interested in is learning to optimize variance of policies that MDPs give you, because sometimes you don't only worry about the expected cost of a policy or expected reward, but how badly the policy can fail or how much reward it can give you in the under optimal circumstances. Another one is analyzing what makes MDPs hard. So in inference, for instance, we have such a measure of tree width that tells us how hard the problem is, and I'm interested in finding an analog of this in MDP. Transfer learning is another. There's a whole range of problems here. I'm interested both in theoretical aspects and practical aspects of it. So transfer learning, first of all, is something you use where you have a domain where you have a lot of training data. It's easy to build a model. And you have another domain where building a model is hard because the training data is, it's scarce, very expensive to collect, and so on. So what you want to do is you want to transfer somehow the patterns of the model from the source domain, from the data-rich domain, into the resource-scarce domain. And so far there haven't been principled ways of doing it, although there has been a lot of work in the field. And I'm interested in how to make this principled and then apply it to fields like medical diagnosis, for instance. Some other work on game theory, how do you make laws more efficient? These days, essentially, laws are built in a way that says everybody should do this, right? Everybody should do the same thing. Okay, this kind of corresponds to enforcing pure Nash equilibria if you view the situations that laws describe as games. Okay, so what happens if we try to design laws that let different people do different things? Okay, again, some rough ideas that I'll be happy to talk to you about. Then applications in crowdsourcing. What I'm interested in here is how do we build workflows automatically? Right now, they're typically designed by humans. And how do we scale crowdsourcing to not simply take, not just to perform tasks that are relatively easy in a cheap way, but how do we make crowdsourcing do something larger than life for us, something that no single human could do in principle. Okay, and again, I'll be happy to talk to you about any of this. But to conclude, first I'd like to acknowledge many people that I've worked with throughout my PhD, and I've learned from a lot. So thanks a lot to all of them. Also, a shameless plug. If you want to know more about the state of the art in probabilistic planning, at least the way it's viewed in AI, my advisor and myself have recently written a book about it, and also have given a tutorial whose slides are on my webpage and on Mossam's webpage as well. So check it out. And to conclude, in my PhD work, I've essentially tried to address two big challenges in probabilistic planning: how to scale up methods of solving existing models, and how to extend the boundaries of what we can model in principle with the current tools. And moving forward, I'd like to work on concentrate on both theoretical and practical work in applying probabilistic planning and machine learning to a whole bunch of problems. Thank you.
Pretty thorough. Any other questions about
Yes.
anything that you said?
What do you think about the applicability of these approaches to partially observable domains?
So, in partially observable domains, sometimes you have a goal, but often these scenarios are sort of reward-oriented. So I would be leading more in the direction of using something like Glutton or Gourmand in these settings. Now, I think another promising direction is actually to use UCT algorithm. I said, this algorithm has a lot of parameters that you need to tune. But if you have a concrete problem, if you have a concrete application, I think UCT has, you can actually tune these parameters, and UCT does have properties that go for it. In particular, if you view solving a POMDP as really just an MDP with a continuous state space, right? It's really an MDP that's hard to solve because you can't perform, say, Bellman backups in a very efficient way. Okay, and to do, you need Bellman backups in MDPs to reason about policies optimally. Now, this is the same issue that you have in ordinary MDPs that have a complex structure. And in those MDPs, UCT has been applied quite successfully. So if you try using UCT in POMDPs, I think you'll have great success.
What about basis functions in continuous spaces?
You can. So again, in continuous spaces, you'll. There has been some work on designing basis functions automatically. People would take, say, a bunch of Gaussians and try to approximate a value function with Gaussians. But yes, you can. You can definitely combine UCT with learning weights for basis functions. Sure. And I think, in fact, some of the competitors in the probabilistic planning competition have done that. Hasn't worked so well quite yet, but there has been work in that direction. Yeah.
In pretty much all of your techniques, I think in all of your techniques, you assume you have a model of the world and that model is correct. There are no errors in it. You've cited a lot of examples, interesting examples where this can be applied in the real world. There, you don't know what the real model of the world is. And so you have this exploration, exploitation trade-off. What do you think about the prospects for taking some of these techniques and transferring them to that tool.
So again, the Gourmand approach that I've described, okay, it's doing something similar to what reinforcement learning approaches do. It essentially does a lot of sampling. Even if it doesn't know the transition probabilities exactly, it assumes that it has some sort of a simulator, real world, for instance, right? And it simply does sampling. So it doesn't, in fact, rely on knowing the problem, all the parameters of the problem in advance. So you could try it there. But again, another kind of approaches that would be directly applicable there are Monte Carlo tree search-based approaches, like UCT. Again, UCT doesn't assume that it knows the model. It just assumes that it has access to a simulator. However, I mean, there is one fine point about UCT. It's inherently a reinforcement learning approach, and what it's trying to do is it's trying to optimize cumulative reward. So in other words, it's not just trying to optimize the cost of the policy that it's getting, or reward of the policy. It's trying to also minimize the cost of learning that policy, right? In planning, you typically don't care about the cost of learning, right? So UCT can actually be made more efficient than it is in its basic form if you only care about optimizing policy rewards.
Let's stop there. Thanks very much.